we'll see today are some other types of applications that we haven't yet considered, some other types of applications of the double integral. And in section 15.5 of Stewart, it includes this application amongst others, right? So today I'm just going to focus on the application of mass, the centre of mass, and related topics, in particular in the context of the double integral. And actually this will be a nice, I guess a nice place to finish our study of double integrals and then move on to their higher dimensional counterparts, the so-called triple integrals. Because in that case, this is what we'll do in tomorrow's lecture when we look at chapter 14 of the workbook. In that case, it's a little bit difficult to visualize higher dimensional volumes, right? And so actually it turns out that considering applications of mass given a density function is a really nice way to generalize to higher dimensions, at least in the first instance. Guys, quieten down, please. At least in the first instance. Okay, so this is the problem we're going to consider in the lecture today, and we'll develop this from a simple one-dimensional model, which I'll talk about in a minute. But say we've got some two-dimensional object whose mass is distributed according to some density function, which I'll call rho, as a function of the two variables x and y. All right, so say we've got some two-dimensional object. In the textbook, in Stewart, and throughout this section, I refer to such an object as a lamina. Okay, some two-dimensional object with mass. All right, so what we'll consider is locating the point of this two-dimensional object. Imagine if we had an infinitely long wire parallel to the y-axis, and if I could pick up this object and place it on that wire so that it was balanced across that wire. So what we're interested in doing is locating the position given the mass distribution rho. All right. Now I'll say plenty more about how we define this density function later on. Okay, but that's what we're going to look for, is that coordinate, that particular value of x on which this two-dimensional object would balance, given how its mass is distributed through a region. And then we ask the same problem if we had a wire parallel to the x direction. We could ask, well, for what value of y could we place that wire? Or in other words, where could we put the two-dimensional object so that it balances on that wire? All right, now see this point where those two lines intersect. So we're looking for balance in this direction as well. And the point where those two objects intersect is called the centre of mass. Right? And so what we're going to do is, I guess, build up the formulae and the concept for this two-dimensional continuum, starting with a one-dimensional rule of or law of nature for a point mass. Okay, so I'll actually go back to talking about some calculus of a single variable function. So we'll start off simple. We'll start off with just point masses, build it up to a continuum in one dimension, and then extend to two dimensions. So I want to give you guys a bit of an idea in this lecture what we can do with double integrals, okay? Beyond just the applications we've seen so far, beyond volume below a surface. Now, we've also seen area of a region in the xy plane, how we can use the double integral to calculate that. But this is yet another application, but it's a bit of a different application, but it's still using the definition of double integral, okay, that we saw way back in, what was it, chapter 7 of the workbook, or lecture 7. Okay, so this is the problem we're going to be addressing in the lecture today. All right, so let's have a look at this law of nature, if you like, that we're going to exploit. So, all right, the picture is, well, here on page 86, it's quite a simple setup. It's like a seesaw, okay, a bit like a seesaw. So say we've got a rod of negligible mass that's balanced on a fulcrum with two masses, M1 and M2, at either end. Now, if it's in balance, so they're balancing, so the law of nature, and this is, I guess, sometimes referred to as the law of the lever, thanks to Archimedes. The law of nature says the distance that M1 sits from that fulcrum, we call that D1, and the distance M2, the mass M2 sits from the fulcrum, call that D2, along with the masses themselves, satisfy this relationship. So M1 D1 equals M2 D2. So this is called the law of the lever. All right, so this is just for point masses. Right? It's just in one dimension, just for point masses. What we're going to do is extend all this to a two-dimensional continuum using integral calculus, right? Using the integral calculus that we've been developing in the lectures over the last couple of weeks, right? So, I mean, this is a very deep lecture today, okay? It's meant to give you quite a deep understanding of the integral calculus, okay, through looking at this application. All right, so anyway, let's just start by, well, building it up one step at a time. All right, so first of all, instead of referring to D1 and D2, instead of referring to these as distances, what I'm going to do is superimpose this system on a number line, right? So I'm going to introduce a coordinate system. Right, so here's the number line. I'll place the fulcrum at this location x bar, right? Let's call it the value x bar. And M1 and M2 will be located at coordinates x1 and x2. So these distances, D1 and D2, so D1, I've just arbitrarily chose to place that to the left. So D1 is just going to be x bar minus x1, with the positive x direction being to the right, I guess following convention. And then D2, this distance, will then just be the difference between these two coordinate values, x2 minus x bar. All right, so we can actually represent that law of the lever in terms of my coordinates now. So we've got M1 times that distance equals M2 times that distance. And what I can do is rearrange this, just using some simple algebra, to isolate this coordinate of the fulcrum, x bar. Right? So I've got an equation now where I can write the coordinates of the fulcrum, or the location of the fulcrum, that's this x bar, in terms of M1, M2, and the coordinates of those two masses. All right, so let's define what these quantities are. These products of masses and coordinates. Okay, so M1, X2, and M2 and X2 are referred to as the moments, sometimes referred to as the first order moments, or just simply the first moments of these masses, M1 and M2 respectively. All right, and clearly you can see in the denominator, M1 plus M2, that's just the sum of the masses. So here, I guess what you could think of is X bar as being some kind of weighted average of the location of the two masses, because it depends on the actual values of those masses as well. All right, so at each step along the way here, we're just going to introduce one more level of generalization until finally we're at the stage where we're at the two-dimensional continuum, okay, rather than just having point masses. All right, so now let's generalize this law of the lever to still a one-dimensional system, but with any number of particles. All right, say with n particles, with masses m1 up to mn. All right, and let's say the coordinates. So again, we'll use this coordinate system I've introduced before. So m1 is located at x1, m2 located at x2, and so on. So what we have then is a law of balance, or apply this law of the lever, but multiple times in order to locate that, that coordinate of the fulcrum, this x bar. So to the left, for points to the left of this x bar. Now at this stage, we can imagine we don't know where x bar is, so all of this is, it's a bit arbitrary at this stage where I place it, but just for the purposes of the calculation, let's say it's at this point. And so the distances, using the law of the lever, the distances will be x bar minus x1, and then multiply that distance by m1, plus, so we take the sum of all these sorts of terms, mass times distance from the fulcrum. Okay, plus x bar minus x2, m2, and so on for all the points to the left of the fulcrum, and this will equal the sum of all these terms corresponding to the point masses to the right of x bar. Excuse me. So in this case, that's just xn. We'll have all these terms of this form, xn minus x bar times that particular mass, mn. All right, so again, we can do something similar, just with a little bit of algebra. We can rearrange that equation to isolate x bar, and again, we end up with this weighted average of the locations of the masses. All right, so in the we end up with the ratio of what's called the sum of these individual moments. We refer to as simply the moment of the system, or the first order moment of the system. And in the denominator, we have just the sum of the masses. So in other words, the total mass of the system in that denominator. All right, so this is for n particles. So you can see for any number of point masses here, we can obtain a formula for the location of that fulcrum in the law of the lever. So this is what we'll call the center of mass of the system. All right, that coordinate x bar. And so this is what we hope to develop in the two-dimensional continuum. All right, so, now let's just have a look at the one-dimensional case. All right, so now we're going to suppose that, that this rod, which we'll just say has length L, that'll become important later on, but it has mass that's distributed according to some density function. Now, in one dimension, mass density, or by mass density, I define that to be the mass per unit length. Or in other words, you might think, okay, I understand constant density, but in one dimension here is just the mass divided by the length. But we're not restricting ourselves to objects of constant density in this case. All right, so what that means is we take the limit as delta x goes to 0 of this ratio delta m over delta x, where delta m is the mass of a small strip of width delta x. Okay, so I guess I could draw a diagram of that situation just to make it a bit clearer. So say we've got our rod of length L, and we divide it up into a number of small segments, each of width delta x. Okay, and so delta m will be the mass corresponding to one of these segments. Guys, there are plenty of seats around. Please take a seat. I'm meant to invite everyone to have a seat. You shouldn't be standing on the stairs. Okay, so what we can do first, I might just, in the first instance, we'll have a look at the law of the lever for such an object. But in the first instance, what I might do is just show you the sort of way we can use integral calculus of a function of a single variable. So we're only in one dimension here. But just to give you an idea how I can obtain an expression for the mass of this object, just given how the mass is distributed, namely for the density function. All right, so what we can do, so this is, I mean, you guys should be very used to this sort of idea, but this is how the integral calculus works. So we've got our definition of density function. In fact, I'll just make it's a slight modification to the text. So here, I've said the object has mass which is distributed according to the density function. Now here I've got the word integrable. What I might do is just change that just to keep it simple to start with, and just say it's continuous instead of integrable. Now, all continuous functions are integrable, so we're only considering a subset of integrable functions. But just to keep it simple, just in the first instance, I'll assume that the density function is continuous. All right, so what we can do to work out the mass of this object, go to one of these segments, choose a representative point, right? This all sounds very familiar. Choose a representative point in one of those segments of width delta x, and I'll call that point x star. Okay, so we've got that the mass along here is distributed according to this function rho of x. Now what I can do is first estimate the mass of this one segment of width delta x, and I'll assume that these segments are small enough. So in other words, I'm assuming that delta x is pretty small, and because I've made this slight modification to the discussion here and said that the density function is continuous, what that means is wherever I choose my representative point, x star, inside that interval, if I move around, if I were to change x star, that value wouldn't change too much, and also the value of the density function at x star would not change by much, right? Because it's a continuous function. So it's not going to be jumping around everywhere, it's just going to be changing continuously. And if I make that interval small enough, it's not going to change by much from one side of the segment to the other. All right, so what I'm going to do just in the first instance is make the approximation that the density is constant over one of these segments, and it takes on the value of the density function rho evaluated at the representative point. Okay, so remember that function's continuous, so it's not going to change much over this interval. Now, if I go back to this definition of density function, which is the limit as delta x goes to 0 of the mass of that segment divided by its width. Now I'm making an approximation, so instead of equals the limit, it's just going to be rho is approximately delta m over delta x, okay, and rearranging that. So here I'll just make a comment in the margin here that rho of x star then is approximately delta m over delta x. Right? I'm assuming that delta x is pretty small, and now I can just rearrange that. I'm assuming it's constant density just over that small segment, or over that small interval, right? Just as an approximation. So I can isolate delta m and obtain this expression for the mass of one of those segments. All right, so now I just repeat this idea over all the segments in the rod and then just add up. Okay, so I'm going to get an approximation to the total mass of this rod in one dimension as just the sum of all these individual masses. All right, so remember, each term here in the sum is an individual mass. Okay, so now it's just a matter of taking that limit as delta x goes to 0, or equivalently the limit as n goes to infinity, the number of segments in our rod. And this is the definition. That's just a Riemann sum, right? This is the definition of definite integral. And we integrate, say we place one end of the rod at x equals 0. We integrate from x equals 0 up to x equals L, the length of that rod. Okay, so here we've got an expression in one dimension that the mass of this object, we know its density function, that is, we know how the density is distributed along the rod according to this density function. Now we can determine the total mass of that rod simply by integrating the density function. All right, now similarly, we can do the same sort of thing for the moments, for these first order moments, all right, as just these coordinates x star times the masses. All right, that's exactly what rho times delta x is, right, in these the approximations over those small segments. All right, similarly, taking the limit as delta x goes to 0, it's just the limit of that Riemann sum, and we end up with this expression for the moment, for the first order moment, so that we can then give a formula for the centre of mass in terms of those objects. Okay, so this is now the one-dimensional situation. So we've started with this simple law of nature for these point masses, right, called the law of the lever, and extended this to a one-dimensional continuum. Now we want to generalize this to 2 dimensions. Okay, so I've got a diagram on page 88 there of at least how we're going to make the approximation. But now let's suppose that we've got our 2-dimensional object, or our lamina, occupies a region D in the xy plane, and we've got a density function. Now we're in 2 dimensions. It's going to have the units of mass per unit area, right? In 1 dimension we had mass per unit length. Now in 2 dimensions it'll be mass per unit area. In fact, generally we're going to be working up to 3 dimensions eventually, not in this lecture. I'll talk about that in tomorrow's lecture. The density in 3 dimensions will be mass per unit volume, right? So now, because we're in 2 dimensions, we're using units of mass per unit area, and so that's going to be given by, and again, I've said integrable density function. So remember what this word integrable means. That just means that the limit of those Riemann sums converge. Okay, that's all that means. But for simplicity, I'll, I guess, specialize to the subset of integrable functions that are the continuous functions. Right, we'll assume we've got a continuous density function, which is a function of 2 variables. So we've got rho of x and y. And now that 2-dimensional density function is taken to be, well, the ratio of mass divided by area, where the limit here is taken as delta A goes to 0. And what we're referring to here is where we take our region occupied by that lamina. So we take our region in 2 dimensions, superimpose this rectangular grid over the object, and then look at each individual grid square and make approximations on the grid square. So pretty much what we did in 1 dimension, but now in 2. Okay, and we're taking the limit as the area of these rectangles go to 0, as let's say delta x in this direction and delta y in this direction simultaneously go to 0. Okay, so now what we're interested in doing is locating that centre of mass, finding that point of balance. And all we'll do in 2 dimensions is reduce the problem to 2 one-dimensional problems. Okay, so it's really not that much of a conceptual leap from the one-dimensional case, from what we saw in the one-dimensional case to the 2-dimensional case. So in other words, we'll apply the law of the lever in the x direction, right? So say we've got this point somewhere, as indicated in my diagram, where there's balance across, I don't know, call it a wire or whatever you want to call that. So we place our object on this wire and we have some kind of balance. So the way we're going to do this is, and as I've indicated in the diagram here, divide the region up into these tiny, tiny rectangles based on this, this grid. choose a representative point inside each rectangle and then measure the distance that point lies from this, this point that I'll call that x bar. Okay, and so we repeat this for all rectangles in our approximation, measuring these distances, choosing a representative point, and then finding the distance. So for these rectangles I'm drawing to the right of this, this value x bar, all right, those distances will always be whatever the x-coordinate is minus x bar. And similarly, when we go over here to the left, all right, and repeat that process, we're going to end up with some kind of law of the lever, but only calculated in the x direction. So essentially we're ignoring the y component completely. All right, now one thing to notice, I'll actually go through a few lines of calculation here, and just in deriving this formula for the coordinates of the centre of mass in 2 dimensions. But just note that the mass in these formulae, in this derivation, that the mass of one of these rectangles is going to be approximately the value of the density function evaluated at our representative point multiplied by the area of that rectangle delta A. Now just have a think about that. Right at the top of the screen here I've written the definition of density function. Now it's exactly the same argument that we used in 1 dimension. All right, I'm going to assume the density function is continuous. All right, so these grid squares that I'm using are pretty small. So when I choose my representative point, I'm going to assume that over that tiny, tiny rectangle, that the density is not going to change much, right, as we move around inside that rectangle. So I'm just going to pick a point inside that rectangle. That's what I mean when I say representative point. I'm going to evaluate the density function there, and I'm just going to say, all right, let's assume it takes on that constant value over that tiny, tiny grid square. All right, so then since the density function here I've got is equal to the limit of the ratio of mass over area, well now I'm just saying as an approximation we end up with the density function is approximately the mass divided by that area, where that constant density function, or rather that constant value that I'm in my approximation, is just the value of the density function at the representative point. All right. So then just rearranging, we end up with the mass must then equal rho times delta A. So that's the approximation. All right. That's why I've got an approximation here. Okay. So we're looking for balance just in this 1 dimension. All right. Just across or in the x direction. All right. So let's have a look. I mean, there's some discussion in terms of the individual masses and moments and so on, but I just want to present it in a slightly different way. So we're only looking in the x direction here. Okay, so in the x direction, so what we'll end up with is an expression. So I'm just going to apply the law of the lever as if it were the law of the lever in 1 dimension, but with many particles. Okay, and so the law of the lever says on one side we're going to have, so the distance from that fulcrum for points to the left will just have the form x bar minus x star, where when I write the starred quantity, that's just the x-coordinate of the representative point. So x bar minus x star is the distance, that's a positive value, multiplied by the mass. Okay, and in this case, the mass is just the density function times the area. All right, and what we're doing actually, I should just make this clear, we're summing over all points, over all these representative points that lie to the left of this x bar. So I'll use a very very sloppy notation, and just under my summation sign, I'll just refer to that as we're summing over all points x star, y star that lie to the left of x bar. And this is just an approximation, all right? So remember that. That's the expression for mass, and that's the expression for distance. All right, so that's like the distance, that's the mass. And then on the other side, we'll sum over all points that lie to the right. Okay, now at this stage, where I put x bar is actually arbitrary, but it doesn't matter. Wherever I put it, wherever it is, it's going to be somewhere. Wherever it is, I'll be able to write an expression like this. But once I do, then I can rearrange it, and what I want to do is isolate x bar and get a formula for x bar. So let's just see what this looks like. In fact, it's going to look very similar. The only difference is that to the right, these distances will look like x star minus x bar, right? Let me just scroll back up for a sec to the diagram. So, here's an example. So in this small grid square, here's my representative point. It has a larger x value than where the fulcrum is. Okay, so that's what I'm summing over here, all points that have that property. So that's the distance multiplied by the mass, which is just density function times area. Okay, now what I can do here is, I'll do one more step. I mean, it's just a little bit of algebra, but I'll do one more step in the calculation. So this implies, now what I'm going to do is gather up all the terms involving x bar, which, by the way, have nothing at all to do with the summation. Right? They don't have the x bar has nothing to do with the summation. So I'll gather up all the terms involving x bar and move them over to the left, and all the other terms I'll put them over to the right. Okay, so to make that, or to rearrange, we end up with all the terms involving x bar, and I can take x bar out of the summation. It's got nothing to do with the representative points, right? So it's just going to be x bar multiplied by, now what's x bar? We've got x bar just multiplied by the individual masses, which are rho of x star, y star times delta A. Okay, so I'm putting all those on the left-hand side of the equation. Oh, and now the line before, I'm summing up, I've got two sums, right? I'm summing up over all points to the left and all points to the right. But once I gather all these together and put them together, right, on one side, I end up summing over all representative points. Okay, so again, my glorious notation here in the subscript of the summation sign, star all. You know what I mean. All right, and what's left over? Well, all the other terms, I'll move to the right. So these are the terms x star times rho delta A, or in other words, x star times the mass. In other words, the first order moments, the things we were calling first order moments before. So that's x star times rho of x star, y star multiplied by delta A. And once again, we're just summing over all points. Because we've combined the two sums over the left, points to the left of x bar and points to the right of x bar. Putting them all together, we just end up summing over all points. This is why it's irrelevant where x bar is, right? And so now we can isolate x bar just by dividing through by this term. Oh, and notice this term is an approximation to the total mass of the system. Okay, so we end up with an approximation which is just the ratio. Oh, we're going to end up with an 88 in our formula somewhere. Sorry about that. So we'll end up with the ratio x star rho of x star y star delta A divided by the other sum, the sum of the individual masses. All right, this is just an approximation though. Guess what we can do? We can take smaller and smaller delta A, right? Or in other words, take smaller and smaller grid squares, take the limit as delta A goes to 0. We've got a ratio of these two terms, which are Remember, rho is continuous, therefore it's integrable. We've got a ratio, or a limit of the ratio, which is just the ratio of the limits. So therefore we end up with this formula. We end up with this formula for the coordinates, at least of the x-coordinate. So let me just write out, just finishing off in the spirit of the calculation that I've just been doing. We end up with the formula for the coordinates, for the x-coordinate of that centre of mass being the double integral of x times rho divided by the integral integral of rho of x, y, dA. So in other words, the integral of these, the first moment of the system divided by the total mass of the system. And similarly, we can go through and do exactly the same derivation in the y direction. So I won't work through it. I mean, the idea is much the same. But let's say we want to work out the value y bar where there's balance. Okay, and we apply exactly the same idea, but just in the y direction, and work out all these rectangles with representative points. Okay, we can work out their distances, and we end up with pretty much the same formula in the y direction. But the only difference is we'll have the first order moments in the y direction, which will be y times rho of x, y, dA. So the integral of y times rho divided by the integral of rho. The integral of rho just being the total mass. All right, and that's what's summarised here. So in the text, we've just written down the individual. So m subscript x. This is it's often referred to as the moment about the x-axis. It's a little bit misleading because actually it's the moment in the y direction, but it's the moment about the x-axis. So that's why, I mean, if you think about what's the formula for the x-coordinate of the centre of mass, it's just like a weighted average, right? So in this case, it's just x times rho over rho. We're integrating both. Okay, so we've got the ratio of these two integrals in each case. All right, so now for some examples, just to see how this progresses. It's really not, well, now we've worked out these integral formulae, it's not that much different from what we've seen up to date. Now we've reduced the problem of locating the centre of mass. Given a density function, we've reduced the problem to just having to evaluate 1, 2, 3 separate integrals. Oh, but there is some good news. These integrals, even we've got to evaluate 3 separate integrals, 3 separate double integrals in this case. But look, note that the region of integration is always the same. So up till now I've been saying the hardest thing you'll have to do in these calculations of evaluating a double integral is to work out an expression for the region of integration that allows you to apply Fubini's theorem. Fortunately, because it's the same region of integration for all the integrals that appear in these formula, you only have to do that once. So even though there are 3 integrals, you only have to work out the region once. Okay, so let's find the centre of mass of a triangular lamina with these vertices. So let's just draw a diagram in the xy plane. We can locate, so the vertices are located at x equals 0, y equals 0, x equals 1, y equals 0, and x equals 0, y equals 2. All right, so here's the region that we're interested in, and we're told it has constant density. So in this case, actually, it's going to work out to be reasonably straightforward because we've got constant density. So instead of rho of x, y in these formulas, we'll just have a rho naught that we can take outside the integrals, and you'll see they cancel in both cases. All right, so now we've got three integrals to evaluate. So now let's work out the expression for this region. So the set of all points with coordinates x and y, well, I can see that the region lies entirely between x equals 0 and x equals 1, right, based on this corner point here. So I can treat this as a type 1 region. Right, they're the regions where the x variable gets constant bounds, and then the y variable will be bounded by, generally speaking, two continuous functions of x. Okay, so I need to put bounds on y now. Now, because I've got these 2 points where the line, which is this boundary of the triangle where this line intersects the 2 coordinate axes, I can immediately see that the equation of that line is just going to be 2x plus y equals 2. Right? So when x equals 0, y equals 2. When y equals 0, x must equal 1. All right, so that's pretty straightforward. And then treating it as a type 1 region, I can see where the upper and lower bounds for the y variable should be, right, given any value of x between 0 and 1. So clearly the lower bound is going to be y equals 0, and the upper bound for y will just be the points on that line. So the thing is, I need to rearrange that and write it as y as a function of x, but I can just write that as y equals 2 minus 2x, and then that's going to be my upper bound. Okay, so I've got 3 integrals to evaluate here. So the integral that's common to both integral formulae for the coordinates is the expression for the mass. And that's just a double integral over the density function. Right? But now in this case the density is constant. Okay, so that's so rho of x and y is just equal to rho naught. Right, which is a constant, which I can take outside the integral. And now what we're left with is this formula for the mass, which is just constant density times the area. Hang on, I already knew that. Right? I didn't have to go through this. I already knew that if I've got constant density, then that really is mass divided by area. So I could have just rearranged that in the first place. But nevertheless, that happened to slip my mind. I didn't mean to do that. It happened to slip my mind, but I still can identify this double integral of the function 1 over this region D as the area of D. Remember that application of double integral. Okay, but this is actually, in fact, this is good. This is a triangle, right? It means I'm not going to have to integrate anything. It's just the area of a triangle. So that's just rho naught times a half, what is it? The height's 2 times 1. Okay, so in this case it just equals rho naught for the mass. All right, so that wasn't too bad. Unfortunately, the other 2 integrals don't work out all that nicely. Well, I mean, they're okay. They're not too difficult. So remember, in the formula for the x-coordinate of the centre of mass, I also need this double integral. Right? I need the double integral of x times rho. But again, rho is constant. So this is just a matter of, set rho equal to rho naught, and I can take that outside the integral, and then it's just a matter of integrating x over the region D. Now I've worked out this expression, so I can apply Fubini's theorem immediately, and because I've set it as a type 1 region, okay, it means we're going to first integrate with respect to y from 0 to 2 minus 2x, right? And then with respect to x, from 0 to 1. Okay, so just an iterated integral now. integrate partially with respect to y. Okay, sub in those bounds. Y equals 2 minus 2x, so that's just x, 2 minus 2x. So you can see, and lower bound is y equals 0. Okay, so you can see we've just got a integrating a polynomial. So just check that that evaluates to 1/3 of rho naught. And similarly, so here's where y times rho. So I need this one for the y coordinate of the centre of mass. And so that's just going to work out to be rho naught by the double integral of y. And then applying Fubini's theorem, integrating with respect to y from 0 to 2 minus 2x. You see, this is the good thing, is I don't have to work out the region of integration again. Again, it's just an iterated integral, and just verify that evaluates to 2/3 rho naught. Okay, so the coordinates of the centre of mass then are just, what was it, 1/3 rho naught divided by the area, the mass, which is just rho naught, right? And for y is 2/3 rho naught. So that's just 1/3 and 2/3. So x equals 1/3. So here's the regions defined between 0 and 1. So there's x equals 1/3. Somewhere there. And y equals 2/3. So this is actually between 0 and 2. So here's 1. So 2/3 might be there. Okay, so there's the centre of mass. And that kind of makes sense for this example. All right, that's a reasonable answer. All right, and this is one thing. You can always just check to see if your answer makes sense. Right? I mean, if we ended up with, say, centre of mass located at -5, 100, you could see, well, it's not actually in the region. It's not in the triangle. Maybe I've made a mistake somewhere. But this answer here makes sense. All right, but we're not always given these problems with constant density. Right? Sometimes we might be given a problem, and I'll just summarise this calculation. So now we've got the problem of finding the centre of mass of a rectangle. So in the xy plane, we're given vertices at the origin, x equals 2, 0, x equals 2, 1, and x equals 0, y equals 1. But now our density function is not constant, but a linear function of x and y. Okay, so perhaps if this was constant density, we would expect it to be right in the middle. But now we would expect the centre of mass to be right in the middle. But that's not the case here. So now this is just, and I mean, applying Fubini's theorem is trivial in this case. Right? So we want to integrate the density function, 6x plus 12y, over that rectangle. We can apply Fubini's theorem straight away without doing any, working out expressions for the region. So x is between 0 and 2, y is between 0 and 1. Right? It's a rectangular region, so all four bounds must be constant in this case. Okay, so then it's just a matter of evaluating these iterated integrals. So you can integrate first with respect to x, then with respect to y. Integrating partially with respect to x, treating y as a constant, right? This should all be familiar. And what about these moments? Well, we need x times the density function to work out the x coordinate. All right, so that's integral from 0 to 1, 0 to 2 of 6x squared plus 12xy, first with respect to x from 0 to 2, and then with respect to y, all right, which evaluates to 28 in this case, and y times the density function. 6xy plus 12y squared dx from 0 to 2, dy from 0 to 1 evaluates to 14. All right, so in this case, the coordinates x bar, y bar. So you guys should check these calculations, right? I mean, they're not too difficult, just iterated integrals. So the coordinates x bar, y bar, so just the ratio of the first order moment, right, 28 over the mass, 24, and 14 over 24. So where does that sit in the in the region? And we can just see if our answer makes sense. So in the region, so the x coordinate is just a little bit bigger than 1. So our x bar will be somewhere here, and the y coordinate is just a little bit more than 1/2. So from 0 to 1 the region is, so a little bit more than 1/2. So the centre of mass is sort of up in the top right-hand corner, or the top right-hand quadrant. And that makes sense, right? Because our density function is a linear function of x and y, so as we move away from the origin, the region is more dense. Okay, guys, anyway, look, one of the main things I hope you can follow in today's lecture was that derivation I went through. All right, see you tomorrow. And I just sent an email out, actually, about Thursday's lecture, which I'm going to cancel, all right, in order to keep in sync with the other stream, which we'll miss out because of the public holiday on Friday. All right, thanks, guys.